Okay, we're back with chapter 4. This particular video is going to um, cover example 4.1. And let's remember that this chapter is on the Bernoulli equation and pressure variation. Example 4.1 comes in section 4.4. So let's jump forward to this particular section. Let's remember that it's on acceleration, and we have a definition for acceleration as being the derivative of velocity with respect to time. And in the notes and in class, we worked out a rather long definition of acceleration. This is the acceleration when we're given a velocity field, and that is a velocity that is a function of position, s. Now, s is along a path line, so this could be, in general, a function of x, y, and z in 3 dimensions, and also time. So the velocity field that we're specifying in this Eulerian approach to specifying the acceleration, this is actually a function of 4 variables, 3 spatial variables and a time variable. And so we work through this equation as we did in the recorded lecture and in class to get this. And we know that this includes both the local acceleration, the partial derivative of velocity with respect to time, as well as these 2 convective terms. One that depends on the velocity with respect to the derivative of position, s, and also the curvature, v squared over r, the centripetal acceleration. So let's skip forward to example 4.1. We're going to be calculating acceleration when we have a velocity field specified. And the particular problem we're looking at is a nozzle that is designed such that the velocity in the nozzle varies as a function of velocity, like this. U of x, where u is the velocity, is u naught over 1 minus 1/2 x over L. U naught is given as the entrance velocity, and down here that is 10 meters per second, so that's a constant. And L is the nozzle length, and this is given as a 1/2 meter. Now, one thing that's very interesting is this problem states that the velocity is uniform across each section. And this is actually a confusing point, because the key word here is across, because we can see that the velocity actually is not uniform in the x direction, but it is if we look at any given cross section across each point of the nozzle. So that's kind of a confusing point. So the velocity in general is not uniform because it does depend on x, but it does across each cross-sectional area of the nozzle. So what we want to do is find the acceleration at the halfway point through the nozzle at x equals L, and I want to make the point that since x over L equals 1/2, not that this matters, but for any part of the problem, but this implies that x equals 0.25 meters since L equals 0.5 meters. Whoops, 0.5 meters. All right, so let's go ahead and make a plan. Our plan is to choose the center line. This is where we're going to calculate. We're going to choose this path line. That's going to be our path line along the center line, because we want to find basically the velocity at the center. And also, we note that our plan, really our ultimate plan, is to calculate the acceleration. And I'm just going to write this as we had before, that this is the equation that we had before. Here's the local acceleration. These were in the tangential direction, and this was v squared. Here's the centripetal acceleration, that's normal. Sorry, that's an n, not an m. Normal direction, and you can look back in the figure. It's all kind of described right here, these 2 directions. And we note now for this particular case that our v is actually u and our s is actually x. And we also note that since we have a nozzle that looks kind of like, if we were to draw a picture of the nozzle, if I can do this, here's a nozzle and here's the center line. We note that for this nozzle, there's no curvature. So R equals infinity, which is going to make the centripetal term 0. So let's rewrite this acceleration now in terms of our variables for this given problem. And we have x, the del u del x, the derivative of the velocity with respect to position basically. And we have the local acceleration, both in the tangential direction, and then we have this. So we're going to evaluate each of these terms in turn. So let's actually just start from the right-hand side. So the first term is u squared over r, and we know that this is u squared over infinity, which is going to make this 0. So there's no centripetal acceleration, and there will be no normal component to it, since it's not curving. The second term is the local, and we note that u is not a function of time, it's only a function of x. So this is also equal to 0. So this is also going to be equal to 0. Now, the third term here is, whoops, let me get a black pen. The third term is u du dx, and this is not going to be 0 because we know that it's that is a function of x. So we have to take u, which is u naught 1 minus a half x over L, and then we still need to find del u del x. So let's do that. Let's find del u dx, del u del x, and then we'll plug it back into this equation up here and multiply it by u. Put some brackets around this guy here. And so this case is, we're going to have, in general, we're going to have this, if we write it out very explicitly, we're going to have this. That's an x. And we know that u naught is constant, so we can bring that out front. And we're left with the derivative of 1 minus 0.5 x over L to the minus 1. We're going to be taking the derivative of that quantity. So this becomes, this derivative is minus 1 times 1 minus 0.5 xl to the minus 2. We have to subtract, well, it's minus 1 minus 1. We have to subtract minus 1 from this exponent. So minus 1 minus 1 gives us minus 2. And then we need to calculate the derivative of what's inside this quantity. And the 1 goes to 0, and we're left with the derivative of minus a half x over L is actually minus a half over L. Now I do want to draw your attention to the fact that the book has an error. The solution in the book actually leaves out this minus sign and shows this as being a positive quantity, which in fact, or a negative quantity, which in fact makes the acceleration negative, which is wrong. So if you check that out, you'll see that there's an error there. So I'm going to go ahead and go to the next slide and pull this all together. If I can do this in my head now. So pulling all this together, we're going to have U naught squared 0.5 over L in the numerator. Note that the minus signs cancel out. We have two negatives. And we're going to have, in the denominator, we'll have 1 minus 0.5 x over L to the third. So now in the denominator we have a third exponent. And this is an x, if I can draw that, yeah. So, so let's plug in for this and see what it equals. So this quantity is going to equal, we know that this is 10 meters per second squared. This is going to be 0.5 over 0.5 meters. And in the denominator, we have 1 minus 0.5 times 0.5, all of this cubed. And so our units are working out nicely because we have 100, that's 10 times 10. This term is 100 meters squared over seconds squared. Meters squared over seconds squared. And these constants cancel out, but we're left with 1 over meters. So we're left with 1 over meters. That's going to be nice because we're going to cancel that one of these meters out in the numerator, and we'll be left with meters per second squared, which is velocity or acceleration. And then this term here, 0.5 times 0.5 is 0.25. 1 minus 0.25 is 0.75. So we're left with 0.75 cubed. And if we now multiply all this stuff out, we're going to have 10 meters per second squared, and 1 over, if I go back here, 1 over 0.75 cubed is actually equal to 2 point, I'm sorry, get myself straightened out here, is equal to 2.37. So the answer to this, and this is actually 100. Sorry, there's an extra 0 in there. So we get 237 meters per second squared. So let's just note that I brought this thing forward wrong. This should have been 100 meters per second squared over here, right here. 100 meters per second squared times 1 over 0.75 cubed, which is 2.37. Multiplying those two together, this is dimensionless. This has meters per second squared. We get 237 meters per second squared. So if we now pull all this together into our acceleration formula here, the acceleration equals, if we remember, u, the other two terms are 0. This is what we get. The u hat direction, if we look back at the original, is in the x direction. So this is going to equal 237 meters per second squared in actually the I hat, or the x direction. Okay, so that is the acceleration, and we can then evaluate this along the path if we want to. We can evaluate it. We can go back and evaluate the velocity if we want. Since the velocity is given as this, we can evaluate this at the total length of the nozzle if we want. So we have a way of calculating the velocity, and also we know that across there we have a constant acceleration through the nozzle. All right, so at least I guess what I'm trying to say is this is at, if you remember, this is at x, the midpoint um, through the nozzle, we have this acceleration. So it's not a constant acceleration, but at this point, at x over L of a halfway through the nozzle, this is our acceleration. Okay, so that's it. And remember that the error in the book is this. This is missing, so they drop a sign, and they get the right answer. The acceleration is in the positive x direction, but there's an error in one of the steps in the book. All right, so that's it for this example.